Okay, so I'm just going to record this little sort of mini lecture on how to write proofs, which I was planning to do at the end of the previous lecture. So I want to discuss two things. So one is, wait, what happened to my, oh, okay. One is how to write proofs. So some advice for writing proofs. Okay. Advice for reading and writing proofs. And the second one is advice for finding proofs. How do you come up with a proof? And these two things are really kind of different, but related. So here are three tips for writing clear proofs. Remember that so a good proof is clear and correct. And clear means a bunch of different things, but mainly it just means that every statement has an unambiguous meaning. So every statement has a clear meaning. And this includes things like every variable that appears in the proof is bound. So in the sense that you know which quantifier, you don't just write a variable x without saying where it came from. And for every statement of a clear meaning, every word that you use has to be well defined. And correct primarily refers to it's logically correct. So every statement follows logically from the previous ones. Sorry, my handwriting is getting kind of bad. And there are other kinds of mistakes, like, okay, the arithmetic and other math that you use is correct. So let's just say the calculations, other math is correct. So here are so I'm mainly going to focus on the first kind of correctness, logical correctness. And here are three tips for writing a proof which is clear and correct. So one is, as you're writing the proof, or before you write the proof, be aware of the beginning, the middle, and the end of the proof. So by the beginning, I mean, these are not formal terms. By the beginning, I mean, be aware of what are you assuming. So what are your assumptions and hypotheses? And this includes what are the definitions of the words that appear in the statement that you're trying to prove. The middle is the argument. So this is the interesting part of the proof, where you use the assumptions and hypotheses to reach the end, which is the conclusion. Now, this seems very simple, but a lot of bad proofs actually come from messing up this basic structure. That sometimes people assume the conclusion, or they assume part of the argument, and then they end up proving. Then they end up with something that's not a valid proof. So when you're writing the proof, always be aware of this distinction. What are you assuming and what are you trying to prove? The second thing is, as you write the proof, use certain keywords that I've been using in class to reinforce and indicate this logical structure. So use some keywords such as, I don't know, assume some variable is arbitrary. So what does that mean? That corresponds to the logical quantifier for all, right? That means you're either trying to prove a for all statement or you're about to apply a for all statement. Another keyword is choose X such that. And this corresponds to there exists. Of course, there are phrases that have the same meaning, like, there exists such that, and so on. Yep.
What about for if-then statements or conditional statements? What would some keywords?
Great question. Yeah. So for if-then statements, well, you could use the word assume. So assume, some proposition, some hypothesis. So this corresponds to it. You're trying to say, hey, I'm about to prove an if-then statement, so I'm assuming the if. And another good keyword, another good phrase to indicate that you're about, where you're going with the proof is we will show that. We will show that, and that would be a conclusion. This is, again, this could be used, this could be saying, hey, I'm proving a conditional statement, or just telling the reader that this, I'm now, this is the goal, right? Some other keywords are, anytime you're using a hypothesis, you could write by the hypothesis, blah, 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 or by the assumption. When you're applying a definition, you could use by the definition of whatever definition you're applying, ... So here you're applying a definition. Another good phrase is it follows that ... or therefore. And here again, you're saying that what I'm about to say is implied by what I just said. And then, okay, there's some additional, you can use these parentheses, forward arrow and backward arrow, to indicate when you're showing a biconditional, to split the proof into the forward implication and the backward implication. Similarly, when you're proving two sets are equal, you may use, A is a subset of B and B is a subset of A. This is to split biconditionals into conditionals and set inclusion into two containments of sets. Okay, so these keywords are what will help both you and the reader, both the writer and the reader, be aware of the logical structure, what's going on logically in the proof. And then, okay, there are some other keywords like without loss of generality, which we discussed yesterday. And this just means you're omitting some, usually some analogous cases, or, well, it just means without loss of generality. It means you're not losing anything by making an additional assumption. And then finally, there's a phrase which I like to use: observe that, or notice that. And this is used to indicate to the reader that, hey, I'm doing something that maybe requires some creativity. I'm not just doing some logical implications that we did in chapter 1. I'm making this is where the creativity comes in. Okay. And then the last thing is always be aware of quantifiers and bound variables. What that means is for every symbol that appears in your proof, you should know where it came from. Was it assumed to be arbitrary? Or did you choose it because you had some you knew that something exists, and so you produced this element? Those two are very different scenarios. So always be aware of these. This is a very common source of mistakes. So those are for now the three main things I want to say about reading and writing proofs. And I want to say one thing about style, which we will develop later in the course. Just hold.
Professor, I think you're muted.
Yeah. Okay, good. So I want to say one thing about style, which is use complete English sentences. Okay. So don't just write equations. Don't just write a bunch of formal logic statements one after another. That's a formal proof, but that's not an informal proof. That's not an English proof. That's not how we communicate with each other. So I'm not going to be too particular about this in the beginning, but by the end of the course, good mathematical writing is like good writing. It should read well. And the other thing is, a lot of people, sometimes it's confusing to know how much to write. Well, you should try to be succinct. Don't write 2 pages if you can write the proof in half a page. But when you're in doubt, like, should I say something? Then say it. Okay. When in doubt, add more detail. For now, it's better to write something a little long that's still complete than to skip some steps. Okay, so maybe what I should do. So, any questions about these 3 remarks?
For the style, the point 1 in style, I remember. So last week I also came to office hour with the question on like, is for all x in for all x parenthesis p a p and pb, is it equal to all x for all x pa and for all x pb, something like that, or it's like implies the single arrow. I think it will be easier to use English to explain, but that English sentence or those sentences would contain a lot of logic.
You're right. So in week 1, we did a lot of this practicing of how to write logical sentences in English, right? So you have for all x, p of x. This corresponds to, for every x, whatever, p of x, right? But you're saying if you have some complicated logical sentence, like for all x, p of x implies, I don't know, q of x, if and only if r of x, then this is correspond to some complicated sentence, right?
Yeah.
That's kind of what you're saying. Yeah. So this was kind of just an exercise in week 1. If it's very complicated, then sure, you can use propositional logic, but most of the time the sentences will not be logically that complicated. You will be able to write them in English.
But what if the question is asking something like to prove that the first
okay,
equal to the second,
right? If the question is asking about logic, then you can use, then you may have to use this formal logic. So okay, so let's say unless the question is explicitly about propositional logic. So I agree. In week 1, we had many statements that really were about propositional logic, and then you had to write these things, and I even wrote them in the solutions.
Okay.
But in the future, even now when we're talking about like sets, we're not going to have as much of this kind of thing.
Okay.
Yeah. But style is for now secondary. Most important thing is correct and clear. Okay, so maybe a good way to, let me just give you some examples of bad proofs. So a good proof is correct and clear. So by De Morgan, a bad proof is unclear or incorrect. And the unclear can come from, undefined words or unbound variables primarily. Incorrect comes from logical mistakes, or other mistakes, but I'll focus on logical mistakes for now. So for example, here's an example of a bad proof. Here's a proposition. The set of rational numbers is uncountable. Here's a proof. So the proof is, I don't know, I came up with a bad proof of this. So the statement is false because it contradicts what we proved yesterday in class. But here's for example, a bad proof. We write down a function by f of n equals n over n plus 1. And then you say, well, f of n is not equal to 2/5. So therefore, f is not onto, and f is not a bijection. Okay, so this is a horrible proof for many reasons. So can anyone tell me what are the bad things about this proof?
There's no English sentences.
Okay, so there are no English sentences. So at least we should add a word like let f be defined this way. Okay, so the bad things are okay. So no, this was not an English sentence. Or I'll just correct it in red. Okay. What else is wrong with this proof?
Does it lose generality because it's assuming one particular function?
Yeah, so there's a major logical error in this, which is this is one particular f, right? But what do you have to show that a set is uncountable? You have to show that for every f from the positive integers to q, f is not a bijection, right? So this is a serious logical mistake, right? That so first of all, we didn't even before saying let, we didn't even specify what the quantifier for f was, but we just studied one specific f. So yeah, we found one specific f, and we showed that that f is not a bijection. And by the way, we didn't even do that very well because this statement is also not quantified, right? We probably want to say for every n in z plus, fn is not equal to 2/5. Therefore, f is not onto, f is not a bijection. But it still doesn't work, right? Because we messed up the logic. We used the wrong, showing that for one f, this happens for one f doesn't imply anything about all f. So this has stylistic mistakes, logical mistakes, and it's a terrible proof. Any more comments on this?
Is there any value to proving a particular case of f, or you should never do this?
I mean, for this statement, it's completely useless. This might be useful for proving some other statement, but it's not useful for this. Yeah, there are other statements, maybe maybe I care about this f for some other reason. So maybe in some context, right? Here's another horrible proof. Proposition is square root 2 is irrational. Proof is square root 2 equals 1.414. What's the next digit of square root 2? 2. Anybody know? 2, I think. Dot, 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 dot. This expansion never ends. So square root 2 is irrational. Okay, what's wrong with this?
The proof assumes that it's irrational, so it is irrational. It's like circular.
Yeah, it's bad in many ways. So first of all, this statement is vague, right? What does that mean, actually? I mean, what does it mean? I mean, it could never end, but it could just be, I don't know, 99999, and then it would be rational, right? So this is kind of it's not a very well specified statement. I mean, if you're just saying it never ends, then it doesn't actually imply that it's irrational. But even if the writer is saying, hey, this has a non-repeating infinite decimal expansion, that was also what we were trying to prove, right? So this is actually a tautology. This is saying square root 2 is irrational because square root 2 is irrational. So the writer confused the beginning and the end of the proof. And so there's nothing in the proof. So this is also bad. And then there's a question of whether the first statement is a sentence. You could make it a sentence by maybe adding a period at the end. It is a statement, square root 2 equals something, period. But that's not good style. But anyway, that's a minor point. The major point is that this assumes a conclusion and just brings some concept from somewhere else, which, namely this decimal expansion, and then doesn't prove it. This is also a logical leap. You can also view this as a logical leap. This doesn't follow from the previous statements, right? Okay, so those are some examples of bad proofs. You can read section 1.7 for more examples. Okay, and I want to end, I guess I've gone over 15 minutes, but I want to end by giving a little bit of advice about how to find proofs. So suppose you have a problem which is I don't know, prove or disprove some statement, right? Let's say it's a statement of type for every x, p of x implies q. And okay, now that we have set notation, let's specify the domain. Let's just say for every integer, something happens. Now, eventually the proof, so let's call this statement S. Now, if you see a prove or disprove statement, the step one is to form some belief about, do you believe S or its negation, right? So write down S and not S. And write down all the definitions, right? So not S in this case is there exists X such that P of X and not Q of X. Step two, write down all definitions. Appearing in the statement S. And now the most difficult step in the prove or disprove maybe is form a belief about S. Do you believe S is true or it's false? And here, a good way to try to form a belief is try some small examples. In this case, X, right? If you find some example for which it's not true, then you're done. And if you find a bunch of examples for which it is true, then maybe you see a pattern, right? So you either find a counterexample foresee a pattern. And now, so step 4 is try to write a proof. Now, what that means is you have some assumptions. You know what the beginning and the end of the proof are, and you have a conclusion, right? And you're trying to get from the assumptions to the conclusion. And in the assumptions, you also have the definitions sitting here. And so just writing down the definitions carefully will tell you some little steps you can take in various directions. Most of these, in many cases, these won't go anywhere, okay? And your goal is to find a sequence of steps that gets to a conclusion, right? So what you're looking for is this one. Now, here, a number of things could happen. Either you find a proof, in which case you're done, or you fail. And if you fail, then you can either revisit step 3, which is maybe the statement you're trying to prove is false. Maybe you learn something from this failure, and maybe you think of some new example, or try a different proof strategy. Okay. Now, so what am I trying to emphasize here? That the process of finding a proof is highly nonlinear. Okay. So remember that the proof itself, the final proof, looks like assumption, some logical steps, conclusion. But the process is some highly nonlinear thing, right? Where you like move around between the assumption and the conclusions in various ways. You take various paths, you get lost, you try examples, you don't even know what you're trying to prove, right? So this is linear, this is highly nonlinear. And this is not specific to proofs, right? This is true in writing in general. When you write something, it reads from beginning to end, but the thoughts that go into doing that are often kind of all over the place. And it's this process of organizing the thoughts that is the art of writing. So don't confuse the two, right? Your thinking process could be, could be pretty complicated. But in the end, when you write the proof, it should have a beginning and an end, and it should be linear. And the other thing I want to say is don't, like, it's okay to be stuck. It's okay to fail and be stuck. As long as every time you fail, you learn something new about what could be the right proof. And it's okay to be stuck. I spend most of my time being stuck. Okay, anyway, that's it. I guess I went way over I hoped for, but let me stop that, and then we can continue the office hours.